Hello calculus students. Arc length, which is if you have some sort of curve and you want to figure out how long it is, I'm going to present really one formula but in two different contexts where what if your curve is presented as a function of x? For example, we have something that passes the vertical line test but not necessarily the horizontal line test, and the curve will start at x coordinate A and end at x coordinate B. In general, if you have just some sort of curve like this and you zoom in on some sort of portion of this curve, like imagine right there, we zoom in, you can make a right triangle out of this. So here's that portion of the curve that we zoomed in on, and I'm going to make a right triangle. There's going to be a hypotenuse, which is a straight line segment connecting the two endpoints of the curve, and then we've got a horizontal segment and a vertical segment. Now the change in horizontal is our change in x, our dx, and change in vertical is our dy, change in y, and we're going to call this red length, this hypotenuse, ds. And you can see that the actual length of this curve we'll call L. As we do smaller and smaller segments, L and ds approach each other. If you break up this curve into a bunch of pieces, and for each piece you approximate how long the curve is, using this L is approximately equal to ds. Okay, I'm going to take the Pythagorean theorem and say, okay, dx squared plus dy squared, right, it's just leg squared plus leg squared equals hypotenuse squared. I'm going to solve this expression for ds. So I'll begin by dividing everything by dx squared. Then I'm going to square root both sides, square root that side, and then this square is gone. And then I'm going to multiply both sides by dx. And so we get this expression that ds is equal to the square root of 1 plus dy dx, so change in y per change in x squared, and then a dx outside of the radical. Now the total length of the curve will be approximated by adding all the ds's up. So the length of the curve will be the sum of adding all the ds's. As we get more and more subintervals, as the number of subintervals approaches infinity, we get an exact value for the length of this curve. So this will be integrated from x equals a to x equals b, and then all we have to do is just plug in this thing right here. This becomes our integrand for calculating from x equals a to x equals b, the length of the arc. Okay, there's the first formula. Suppose your curve is presented as a function of y, so something that passes the horizontal line test but not necessarily the vertical line test. Well, here you want to establish the beginning y coordinate, y equals a, and the ending y coordinate, y equals b. Then we start with the exact same setup. So we start with the same Pythagorean theorem, but this time I'm going to divide everything by dy squared. So we have dx over dy quantity squared plus 1 is equal to ds over dy quantity squared. Then I'm going to square root both sides and then multiply the dy to the other side. So you get ds is equal to the square root, and this is a sum, so it doesn't really matter which one I write first. I'll write 1 plus dx dy squared and then a dy at the end. And then the length of the curve will be the integral from y equals a to y equals b of ds, which is going to be the integral from y equals a to y equals b, and then this integrand. And here's the formula for finding the length of a curve if that curve is presented x as a function of y. Okay, as our first example, find the length of the curve given by y equals natural log of x over the interval from 1 to 3. Y equals the natural log ln of x, and I'm going to crop it using curly brackets. Let's go from 1 to 3. So we're really just looking at the length of this curve right here. If you were to just approximate it, it looks like it's clearly longer than 2 units, but it doesn't seem to be as long as 3 units. Since y was presented as a function of x, we're going to be using this first formula right here. So in this particular example, since we know that y is equal to natural log of x, we have to find dy dx and plug that in right there. So y is the natural log of x, therefore dy dx, which is just Leibniz notation for the derivative of y with respect to x, is 1 over x. Specifically, our integral becomes an integral from x equals 1 to x equals 3, square root of 1 plus and then 1 over x squared dx. Okay, there are several ways you could integrate this, but I don't see a basic substitution being helpful. I'm going to have to do a trig substitution to finish this out. And notice we have a sum of squares going on inside of here, and then square root of that. Sum of squares makes me think trig substitution, and this is the case where we want whatever's being squared here, which is 1 over x, to equal the square root of that number, which is 1, times the tangent of a new variable u. So this is our trig substitution that we'll be using to finish this problem. I'm going to go ahead and solve this for x, and then I'm going to differentiate both sides. So if I just invert both sides, by the inverse I mean the reciprocal, you get cotangent of u, and then differentiate. So dx is equal to negative cosecant squared du. I'm not going to change the limits of integration. I'm going to leave them 1 and 3 and just make sure I get my antiderivative back to x before I plug them in. So I'm going to proceed without limits on my notation for now. I'm going to change this part here to tangent of u, and the dx we're going to change to negative cosecant squared du. 1 plus tangent squared is secant squared, and then you can square root that and just get secant. I'm going to pull the negative out of the entire thing, so it's negative integral of secant u times cosecant squared of u. If I change everything to sines and cosines, it would be cosecant's 1 over sine. So I see a 1 over cosine here and a 1 over sine squared here. That might get me somewhere. Other things I could explore, maybe do a Pythagorean identity on this. We know cosecant squared is equal to 1 plus cotangent squared. I think I'm going to go that route and see what happens. So use the Pythagorean identity right there. Cotangent is cosine over sine. This is 1 over cosine, so when I distribute it, I'm going to get some simplification. So that's what I'm going to do for that part. I'm going to leave this negative out front for now, distribute this here, and break this up into 2 different problems and see where it goes. So we have a negative integral of just secant u plus secant u cotangent squared u of du. Now this antiderivative I know, that's memorized. This one I'm going to change the sines and cosines and see how it simplifies. This is a 1 over cosine, this is a cosine squared over sine squared. So looks like we're going to get a cancellation of some cosine, so 1 cosine will be left up top and you'll have a sine squared left in the denominator. This is doable because I see a u substitution, or actually a new variable, a w substitution working here. I'm going to let w be the sine of u, therefore dw will be the cosine of u, du, and you can see we have a dw over a u squared. This part here I'm just going to do with a memorized antiderivative, and don't forget to distribute the negative. The antiderivative secant is natural log secant u plus tangent u. And then distribute the negative, so minus, and we'll have an integral of a dw over w squared. We anti-differentiate that using the reverse power rule, plus 1 over w. Now I'm going to change that w back to sine of u. And now to finish this out, I'm going to need a reference triangle. Okay, so u is an angle, and we want the tangent of u to be 1 over x. So if I do the opposite is 1 and x is the adjacent, Pythagorean theorem gives me the other side, 1 plus x squared, all inside a square root. And now I have a reference triangle to do my back substitutions. Okay, so we have negative natural log. The secant of u is reciprocal of cosine, so it's hypotenuse over adjacent. The tangent of u is 1 over x, plus, and then the sine of u is 1 over the radical 1 plus x squared, but I want to reciprocate that. So it's just going to wind up being plus the square root of 1 plus x squared. I'm going to go ahead and now bring in, again, the evaluation bar. We can evaluate from 1 to 3. Okay, so plugging in the 3 first, we get a radical 10 over 3 plus a third plus a radical 10 minus, plug in a 1, you're going to get a radical 2 over 1, so just a radical 2. Plug in a 1, you're going to get a plus a 1 plus a radical 2. If you want to distribute that negative through, do that work with a negative distribute, so you get a plus here and a minus there. And there really isn't much more I expect you to do with this one by hand, but if you were to reach for a calculator and decimalize this, you would get about 2.302. I'm going to type in this integral right here and then see if it gives me this decimal. int, we're going to integrate from 1 to 3, square root of 1 plus, and then parentheses, we had the 1 over the x, then put a square on that, then get out of the radical, and then put the dx. And there's our 2.302 approximately. Now, when it comes to doing these types of integrals, they all have the same structure as a square root of 1 plus and then a derivative being squared. Very often, the way to resolve this will be to do a tangent substitution like you see right here. Find the length of the curve given by y equals the square root of 9 minus x squared over the interval from negative 3 to 3. I'm going to say f of x equals, instead of y, so I can refer to the function f later, square root of 9 minus x squared. Oh, strange, it looks circular, doesn't it? Top half of a circle, and it is. Y equals the square root of r squared minus x squared is the top half of a circle centered at the origin with radius r. So this is radius 3, centered at the origin, and just the top half. So we're really trying to figure out the length of this curve, which is half the circumference of a circle of radius 3. So I really don't need to do an integral to answer this particular question. This radius is 3, so the circumference of an entire circle is 2 pi r. So 2 pi times 3, so 6 pi. But then we cut that in half because this is only half that circle. So I expect an answer of 3 pi out of this. But let's go ahead and do the integral and see what happens. I'm going to just use the line that's up here already. But instead of having this 1 over x in there, I'm going to put a f prime of x. And we need to change our limit not from 1 to 3, but from negative 3 to 3. Now, we did just say that this should be an answer of 3 pi. Let's go ahead and just do 3 pi and see what that is in decimal. And look at the two answers. So roughly 9.4 units long is how long this arc is. Okay, let's go ahead and do this one by hand though. So I need to find what dy dx is. This is another case where the function is presented as a function of x. To find the derivative of this, think of this as instead of the square root of being 1/2 power, and use a generalized power rule. So 1/2 is going to come down, 9 minus x squared repeats, new power is -1/2, and then the chain rule, multiply by the derivative of the inside. If I were to simplify this, it looks like it's going to be -x over the square root of 9 minus x squared. Also, because that I see that this function is an even function, because if you plug in negative x's, you get the same result as if you plug in positive x's because of that square, that whatever it's doing from -3 to 0, it's going to repeat from 0 to 3. So I could use some symmetry and say that the length of this curve will be double, but then integrate only from 0 to 3. And the formula is the square root of 1 plus, and then we put the dy dx, which is -x over radical 9 minus x squared, and that needs to be squared, and then a dx outside that. So our length is equal to 2 times the integral from 0 to 3, square root of 1 plus -x gets squared, becomes just x squared, and then that radical becomes squared, so just 9 minus x squared. Next thing I'm going to do is get a common denominator. Where that 1 is, I'm going to replace that 1 with 9 minus x squared over itself. Adding the two numerators together, notice the x squares cancel, so you get just the 9. And the square root of 9 you can do separately, so you get 3 up top, over the common denominator, which gets square rooted. And here, we have a difference of squares here, so I'm going to use the sign version of our trig substitutions. The thing that's being squared is x. I want x to be the square root of that number, which is 3, square root of 9 is 3, times the sign of a new variable u. dx, therefore, will be 3 cosine of u. I'm going to leave the limits of integration 0 and 3. I'm not going to change them. Make sure you get your antiderivative in terms of x before you start plugging in 0 and 3. All right, so our length of the curve is equal to 2 times an integral from 0 to 3. Make these changes. We have 3 over radical 9 minus 9 times sine squared of u, and then times a 3 cosine of u du. Oops, I forgot the du down here. We get a 9 cosine of u up top. And the bottom is, I can factor the 9 out, take its square root, that makes it 3. And then that leaves a 1 minus sine squared inside the radical. But 1 minus sine squared is cosine squared and inside the radical, so it just becomes cosine. Now we get a cancellation of 9 over 3 becomes a 3, multiply it to the 2 to the outside, so we get length is equal to 6 times an integral from 0 to 3 of just really 1 du. And the antiderivative of that is not x, be careful, you gotta look to the differential. The antiderivative of 1 du is u. So we get 6u out of this that we're going to evaluate from 0 to 3. Don't plug 3 and 0 in for u though, those are x coordinates. So we have to do a back substitution. Returning over here, solve for u, you get u is equal to, let's see, divide both sides by 3 and do the arc sine. It's the arc sine of x thirds. So our length is equal to the arc sine of x thirds evaluated from 0 to 3. Plug in 3, we get arc sine of 1, minus plug in 0, we get arc sine of 0, and I'm forgetting a 6. And the arc sine of 1, that means we're trying to find an angle between negative pi halves and pi halves where the sine is 1, and that happens at pi halves. And the arc sine of 0 will be 0, so just minus a 0, and then 6 times pi halves is 3 pi. So that confirms the 3 pi answer we got using geometry. Which makes you wonder, why do we bother doing this if I could just do a geometric approach? Right? If I look at this graph and say, oh, we're just trying to find the length of half of the circumference of a circle whose radius is 3, we got 3 pi very quickly with that line of thinking. But what if this had been find how long it is from -2 to 3? Now all of a sudden I don't have a clear fraction of the circle. When it's in the entire top half, it's easy. But when it's a portion of the circle, which proportion we don't know, then the only way to do this really that I know of is with the integration. Okay, this time I'm going to present x as a function of y. So we have a sideways parabola like this. So we're going to use the other formula for arc length. So here's our formula we plan to use. See, from the point 1, -1 to the point 4, 2. So 1, comma, -1 to the point 4, comma, 2. Okay, so we really want just a portion of this parabola. Well, because this is presented x as a function of y, all that really matters is that I know the y limits of integration. So that's y equals -1 up to y equals 2. Don't integrate from 1 to 4. Those are x coordinates. Also, I need to find out what dx dy is, so let's do that now. What's the derivative of x with respect to y? Let's differentiate that, and you get just 2y. And that's what's going to go in right there for that spot. So our integral becomes an integral from y equals -1 to y equals 2, square root of 1 plus, and then put a 2y in there, and a square, and then a dy. Now, what I would do next, to do a trig substitution, I would let 2y equal the tangent of u, and then go from there. I'm not going to do this one by hand, although I encourage you to do it by hand and just go straight for the integral calculator to get an approximate answer. It's about 6.1257 units. Not units squared, not units cubed, right? None of that, just units. Length units, that is. Okay, and that's how you would approach finding the length of a curve where x is presented as a function of y.